Hello, this week we're going to be talking about probability in the normal distribution. This was a slide that I showed at the very beginning of class, and it shows the two different branches of statistics. There's descriptive statistics and inferential statistics. So far in class we've been going over descriptive statistics, and now we're going to step to the other side, to the other branch. Now we're going to be starting to cover inferential statistics. So we've been describing data, descriptive statistics. Some of that has been central tendency and variability. From this point on, we're going to be focusing on decision-making statistics, which is AKA inferential statistics. So think about it for a second. What does it mean to make an inference about something? It means to draw a conclusion. So people use conclusions to make decisions. So inferential statistics is also called decision statistics. Inferential statistics is based on something called probability theory. Probability theory is a very important part of inferential statistics. So we are going to start by learning this first. So probability means chance. What are the chances something will happen? So a simple example is, what is the probability of getting tails on a coin flip? 50-50, right? Because there's a heads or there's a tails. Another example, a more empirical probability example. Empirical, again, means that it's observable. So based on long-term observations, you might have a probability about how often a home team is going to win a football game. So based on previous evidence or previous observations, you might have there might be a 60 out of 100% chance that a football team is going to win while they're at home. So a probability always ranges from 0 to 1. If it is closer to 0, that means it's pretty much impossible. And if it's close to 1, it means that it's very certain that it's going to happen. So in the 0 to 1 will make more sense in a few minutes when we actually calculate some probabilities. So when is probability helpful? It's helpful when you are trying to predict any random event. So a random event is any event where the outcomes observed in that event can vary. It's not really necessary to use probability in the instance of a fixed event or an event where the outcomes observed in that event is always the same. Because the whole point of probability is to be able to make a prediction of what you think is going to happen. So if something's not going to change because it's a fixed event, there's really no point in using it. So let's watch this video for a second, which will give some examples of when you could use probability theory.
On the role of probability theory in machine learning by building a spam classifier from scratch. Life is full of uncertainty. We try things which we think will probably succeed, but we're not certain. Will it rain today? Is it okay for me to dance in public? Should I invest more time in this relationship? Probability theory gives us a framework to model these decisions, and by doing so, we can make them more efficiently. There exist branches of math that help us make decisions when we have perfect information, but probability trains us to make decisions where there are indeed observable patterns, but also a degree of uncertainty, aka real life. It's a measure of how likely something is to happen, and the practice of analyzing events governed by probability is called statistics. A simple example is flipping a coin. There are only two possible outcomes, heads or tails. We can model the probability of heads happening since we know two things, the number of ways that can happen and the total number of outcomes. We've got a 50% chance in this case, just like how often Bluetooth decides to work. This is a random variable.
Okay, that was a silly video, but it was kind of fun. All right, so to calculate probability, again, the definition of probability is the chances something will happen. So how do we find it? It's this equation right here. So before you can even calculate it, you need to know both numbers. So you need to know the number of times an event can occur out of the total number of times any event can occur. So for example, in that coin situation, the number of times an event can occur was 1, and we know that the total number of times that event can occur is 2 because there's 2 sides of the coin. So here are some examples below. Number of times you could roll a 3 out of the number of sides of a die. Number of ways you could pass a class out of number of ways you could fail a class. Number of female jurors out of number of total jurors. So these are all different ideas of times when you could calculate probability. So to solve these examples right here, that's what we're about to do now. So the equation is listed. It's right here. Number of times an event can occur over the total number of times any event can occur. So when you do that and you want to check yourself to make sure that your answer is correct, always know that probability varies between 0 and 1. So we already talked about this, right? So if you get a number outside of 0 or outside of 1, know that you need to redo it because you didn't calculate it right. And then also know that probability can never be negative. But again, to repeat, once you once you actually do the formula for these, know that the closer to 1, the more probable an event is, and the closer to 0, the more improbable an event is. So let's go ahead and do them. So number of times you could roll a die, number of times you could roll a 3 divided by the number of sides of a die. So you can only roll a 3 once because there's only one side that has 3 on it. However, there are 6 sides of a die, so 1 out of 6 equals 0.16. 0.16 is closer to 0, so the event is less probable that that's going to happen. Let's look at another example. Number of ways you can pass a class, A through C. So you can get an A, a B, or a C. Number of ways you could fail a class is D through F. So that's 2, but the total number of ways is 5 because there's 5 scores, A, B, C, D, F. So 3 out of 5 is 0.60. 0.60 is closer to 1, so the event is more probable. Number of female jurors out of total number of jurors. So this would just be something, maybe this is in a city or something. You would get this information from your city or from a website. So there's 7 female jurors out of the number of total jurors is 12. So that's 0.58. 0.58 is closer to 1 than it is to 0. So the event is more probable. All right, so here's some more examples. So here we have, so negative, we have a bridge of death, okay? And we have 10 different people over here that are gonna cross this bridge. And so it looks like 1, 2, 3, 4, 5, 6, 7 died after they crossed the bridge, and 1, 2, 3 lived. So based on this data, what is the probability that any one person will survive crossing? So crossed alive, it was 3 out of the total amount is 10, it was 0.3. So because it's closer to 0, that means it's not very probable that they're going to live. So you go ahead and do the next one. What is the probability that any one person will die crossing? So if you need to take a minute and pause, you can do that. Alrighty, and the answer is 0.7 or 0.70. So this is closer to 1, meaning death is more probable. So here's another example. So go ahead and press pause, and then when you're ready, the next slide will have the answers on it. And here are the answers. So I want to let you know that what we just did, we did pretty simple calculations. There are some other rules when calculating probability when you're trying to do different types of scenarios. So there's the converse rule, the addition rule, the multiplication rule. You know, you don't really do this kind of stuff a lot on the day-to-day in terms of statistics, and I'm kind of more of a big picture statistics gal versus getting into the nitty-gritty details. So if you want to learn this stuff on your own, you are more than welcome to in the book. But I think we've given you a good taste of what probability is, and the importance is that it needs to be a number between 0 and 1. That's kind of the big thing you can take away from this conversation. Excuse me, from this lecture thus far. So yeah, again, so here's the slide. Just remember all possible outcomes always equal to 1. So the example of the coin, there's a 50-50 chance, 50-50, that equals to 1. The example of the life or death, so there was a 30% chance and a 70%, 30% of life, 70% of death, so that equals to 1 or 100%. All right, so now let's talk about how does this, everything we've talked about so far, probability, relate to the normal distribution. So the normal distribution is in fact a theoretical probability distribution. So this is a probability distribution, so they're extremely related. The normal distribution is an ideal model. It's not necessarily the way things are, but the whole area of the distribution is equal to 1. So similar to here, equal to 1, so is this. This whole area right here is equal to 1. So that's important to remember as we go forward. Okay, video time. So this is a video that kind of brings home the idea that this whole area of a normal distribution is equal to 1. So I want to watch that first. So let's go ahead and do that now.
I've created this preface to the video on the normal distribution to help people who might have forgotten.
You know what? I don't think that's the right one. I think it's this one that we wanted to do first. Actually, I don't have it up. Let me bring it up. Okay, here we go.
All right, I want to show you what a normal distribution is all about in statistics. And there are 3 things that should come to mind when you read the words normal distribution. The first thing is that you have what's called a bell-shaped curve that basically looks like this right here. It's a bell-shaped curve, okay? That means that the mean, which is kind of sitting right here in the middle, has the most data that's sitting around it on either side of the mean. I'll talk a little bit more about that later. But definitely, bell-shaped curve is one of the first things that should come to mind when you read that word normal. The second thing that should come to mind when you hear normal distribution is that the total area under the curve is equal to 1. So all of this area underneath this bell-shaped curve, all of it, including everything out here in the tails as they get smaller and smaller, is a total area of 1. And there's one more thing. The third thing that should come to mind is that this bell-shaped picture here is symmetrical, right? It's symmetrical. And that comes into play and is very handy. It's kind of a geometric term for later problems. So if I was to kind of split this thing right down the center here, you would see that half of this picture over here, if the whole thing is 1, is 0.5, and the other half is 0.5, giving you a total area, everything from here all the way over to here, Right? Total area all together, everything under the curve here, gives you a total area of 1. So those three things should come to mind when you hear the words normal distribution. It's bell-shaped, total area is 1, and it's symmetrical.
All right, so I just wanted that to drive home the idea about this being an area equal to 1. Okay, now he just talked about in terms of 50-50, right? So 50% here, 50% here. We don't use those percentages as commonly as we use these ones right here, this 34.13, 13.59, 2.14. So that's on both sides. So this next video explains it in terms of these percentages broken up in that manner. It also talks about standard deviation, which we discussed last class. So it kind of brings home last week's material and this week's material. So, and then in addition, it starts to talk about something that we are going to cover the remaining of this lecture about, which is z-scores. So anytime the person making this video talks about z-scores, don't worry about it. We're going to bring it up in a few minutes. So let's watch this video for about 10 minutes. Oops.
Some basic elements of statistics, appreciate the contents of the video, because the video does assume some basic knowledge. For example, this video on the normal distribution assumes that you already know 3 measures of central tendency, and in particular the mean. And if you already know what an average is, then you'll know what the mean is, because the mean is the term that statisticians use for the average. In addition to the mean, there's also the median and the mode. So these are basic measures of central tendency, and I assume that you understand in particular the mean already. I also assume that you know what a standard deviation is. And so just as a very brief refresher, a standard deviation is a measure of variability. And in particular, it represents the average dispersion of data relative to the mean. So if you don't understand what a standard deviation is, I encourage you to check out one of my videos on the standard deviation or somebody else's videos on the standard deviation. The key thing to know about a standard deviation is it's measuring variability, and specifically, it's the average dispersion of data relative to the mean. Now, I also assume that you know what a histogram is. And just to refresh your memory, a histogram is a diagram that consists of rectangles. And each rectangle represents the number of observations associated with a particular value on the scale of interest. Now I'm going to show you an example of a histogram in a minute, but before I do so, I just want to mention 2 aspects of a histogram that are really important. First, an x-axis, which represents the continuum of the scale of interest from low to high, and the x-axis goes from left to right on the histogram. And there's also a y-axis, which represents the continuum of observations from 0 to some maximum. So here's an example histogram, and here are those 2 sides. I have the x-axis on the horizontal going from left to right, and here is the y-axis, which is vertical, going from 0 to some maximum, which in this case is 800. And this is the histogram of sleep. These are actual data from a real study. We can see that in this histogram, the range goes from 2 to 12 on the x-axis. And there's also a frequency axis, which goes from 0 to 800 frequency or observations. And here are the rectangles that actually make up the histogram. And so in this case here, 7 hours of sleep corresponds to something like 710. 710 people responded that they sleep 7 hours a night. And then on this little rectangle, it's something like 375, say. So each rectangle represents the frequency of observations in the data file that correspond to a particular value on the x-axis. The mean for these data is actually 7.31, and the standard deviation, the measure of average dispersion, is 1.21. So with knowledge of the mean, the standard deviation, and a histogram, you should be able to appreciate this video. In this video, I'm going to talk about the normal distribution. I'm going to explain what it is by looking at an example of a very ideal normal distribution. and some of the properties of that normal distribution, and then I'm going to give an example of a real-world normal distribution. Okay, let's get started. This is what a normal distribution looks like just with the normal curve. And this is where, if you look at it, you can tell that it has a bell shape to it, and that's why some people call it a bell-shaped curve. And people use the term bell-shaped curve synonymously with the normal distribution. Now, when people talk about a normal distribution, particularly within a standardized score format like z-scores, the middle, or the mean, or the median as well in the normal distribution, because they're equal, is often represented with a 0. And so a z-score has a mean of 0 and a standard deviation of 1. And if you're not really totally clear on z-scores or how to calculate them, I've got a video on that I encourage you to check out. But I'm also going to talk about it here as well. So if you go in terms of standard deviations within a normal distribution, in terms of 1 plus standard deviation or 1 negative standard deviation above and below the mean of 0, you know for certain with a perfectly normal distribution that there are going to be 34.13% of the observations are going to be between 0, the mean or median, and in the normal distribution case, the mean and median are exactly the same. Between 0 and negative 1, you're going to have 34.13% of the scores. And conversely, between 0 and plus 1, you're also going to have 34.13% of the scores. So in total, you get 68.26% of all observations within plus or minus 1 standard deviation away from the mean. So the majority of people, in fact, a little more than 2/3 of people on a number of criteria, like height, like intelligence, a number of properties in the behavioral sciences and outside the behavioral sciences, most people are between 1 standard deviation below and above the mean. In fact, it's a little more than 2/3. Now, if you keep going further in normal distribution, such as -2 and +2 standard deviations above the mean, you'll find that there's 13.59% of observations between -1 and -2, or +1 and +2. For a grand total, if you push out from -2 all the way to +2, you get 95.44% of observations between -2 standard deviations and +2 standard deviations within the normal distribution. And that's where 1.96, the value of 1.96 is very commonly used in statistics, in particular for a z-test when you're testing the difference between a sample versus a population. We use a z-test, and the demarcation criterion for statistical significance is a z-score of 1.96. And that's because 1.96, which is just a little bit less than 2, actually corresponds to exactly to 95% of the total normal distribution. So there's actually 5% left over on the two tails for an alpha level test of 0.05. And that's where that 1.96 comes from. We could create a 1.96 here and a negative 1.96 here, and that would correspond to 95%, that section of the normal distribution.
25 million bookable rooms in hotels, resorts.
Now finally, the last sections that I'm going to talk about, because obviously the distribution is asymptotic, which means that the line just keeps going infinitely. In the last section of the most commonly used standard deviation demarcations in various disciplines, which is 3' standard deviations, we have 2.14% of the people or observations between -2 and -3, and then we also have 2.14 between +2 and +3. And that makes for a grand total of 99.72% of all observations in the distribution. And just like there is a correspondence between 1.96 and 95%, we also come across the value of 2.58, which is probably somewhere about here. So 2.58 and -2.58 about here, and that would correspond to 99% of the total distribution. And so if we needed to build 99% confidence intervals on a number of statistics, we would use the value of 2.58. Why? Well, it's because that value corresponds to that section of the distribution in order to represent 99% of all observations in the distribution. So that's what a normal distribution looks like theoretically. And this is what the z-scores correspond to in terms of each section of the standard deviations and the percentage of observations in those standard deviations. Of course, any scores could be under here. You could have intelligence scores. It would be 100 and a standard deviation of 15. So 100 would be here, 115 here, and 130. And then we just keep going. 145 would be this section of the normal distribution. So very few people, if this was 130 IQ, 2 standard deviations above the mean is 130 for an IQ score. Very few people have an IQ score greater than 130. We can see that it corresponds to something a little more than 2.14%. There's another percentage here, and you can calculate that in your mind. It would be something like half of the 0.3, but it goes on infinitely. So very few people have an IQ greater than 130. It's only about 2 out of 100. Actually, I had that there, 0.13 on each side. What a normal distribution looks like in reality, this is data that were simulated from a computer program to generate normally distributed data with a sample size of 1,000. This is what it looks like. And it doesn't look perfect. There's a section here that looks like it's sticking out. You can tell it's just not that really smooth, perfect normal distribution. Now, had I created it with 10,000 people, it would look better. But in reality, this is what kind of data we get in practice. And you might be looking at that and you're going, well, is that really normal? Or is it statistically significantly different from normality? And that's where we have statistics to help us test those kind of hypotheses in practice. So we've got tests like the
Okay, so I wanted you to watch that video. I know some of what he went over was over what we've learned, but I wanted you to see that video because I liked how he described the breakup in terms of percentages in the normal distribution, what's used most often, and how he also ties it to standard deviations. So those are the two things to really have gathered from that video. What he's talking about in terms of z-scores, we are going to learn that now, or in a few minutes. So why do I really want you to know about these percentages, and why do I really want you to know about standard deviations? Why is the normal distribution so important? Well, the proportions or the percentages of the breakups right here and a normal curve apply universally to any data set that is normally distributed, meaning the average or the mean is always in the center, so that's a normal distribution, and as long as it is, then these rules apply in terms of proportion. So majority of the people are right here in the middle, right here in the 2/3, and then anything outside of it is more unique. And also standard deviation, being able to speak in standard deviation units is widely understood. It's a widely understood measure for distance from the mean to various data points above and below it. So it's helpful to speak in the language people understand. Again, statistics is a decision science. Us as social science researchers, we are interested in studying humans, studying their behavior, studying how it impacts society. That way we can make decisions to be able to better the world. So speaking in standard deviation units, +1, +2, +3, these 1, 2, or 3 are -1, -2, or -3 standard deviations from the mean. Most people know that language, so it's important to be able to speak the same language as decision makers. So now let's move on to z-scores. So like I said, the man in the last video spoke about this some, so now we're going to learn it. So a z-score is the number of standard deviation units from the mean of a single data point. So just one data point. So z-scores range from -3 to +3. So here's -3 to +3. And they're important because you can compare different scores from different data sets in a comparable way since they are reported in the same standard deviation units. And I'm going to describe that at the very end of this presentation. So how to calculate z-scores. The equation is the score itself, so the raw score minus the mean divided by standard deviation. You can also see it pasted here in symbol format. So a few classes ago, we learned how to calculate a mean. Last class, we learned how to calculate a standard deviation. So let's take one raw data score from last class when we were doing the 5-step process to find the standard deviation, and we're going to use it now to plug it into this equation. So as a reminder, this was our data set from last class that we did that step 1 through 5 in. And so let's just choose any number to be able to plug into this z-score calculation. I am actually going to be choosing 31 for us. So this is a raw scores representing age at first marriage for a sample of 25 adults, but we are particularly going to be looking at this raw score of 31. So we can go through the 5 steps we learned last class to find the mean and standard deviation because those are required for the equation. We have the score of 31, but we need to know the mean and standard deviation of this data set. So we can go through steps 1 through 5 again, or we can just use a calculator. So let's go ahead and use a calculator. So I am going to grab all of this data right here and plug it into this little guy. Okay, so our mean is 23, and then our standard deviation is 3.81, which I think we rounded up. Let's look. Yeah, rounded up to 3.82. So we just plug in those two numbers. So plug 31 into the z-score equation. So score 31 minus the mean was 23 divided by the standard deviation of 3.82 equals 2.09. So that is our z-score for the raw score of 31. And the z-score represents the distance away from the mean in standard deviation units for one score. So let's look at where that z-score 2.09 would be on a normal distribution. So 2.09, here's 1, 2, I'm guessing it would be probably around here, 2.09. It's a little bit above the 2. So as a reminder, our mean was 23, right? That was our mean. So the mean is at this threshold right in the middle. So, and the score that we were interested in is a 31, and 31 was placed at the 2.09 standard deviation spot. So let's just go ahead and calculate that. I'm going to guess, and for this data set right here, the increments in which the standard deviation went up in, right here, 3.82. So each standard deviation went up by 3.82. So 3.82, and then it went up by another 3.82, and then it went up by another 3.82. Or in the case of the negatives, it went down by 3.82, another down by 3.82, another down by 3.82. So that was our standard deviation, and then so yes, let's see. So here at the 2 standard deviations at 7.64, but remember we're 2.09, so we're a little bit above 7.64. So I'm just going to go ahead and say it's 8. So let's see if that adds up. So 23 plus 8 equals 31. So you can see how that score, the z-score, explains the placement of the raw score in terms of standard deviation units away from the mean. So it makes sense, right? So here's a reminder of our data. 31 was the highest number in the data set, thus being over the second threshold. It is in the top 2.14% set of scores, so that makes sense, and that's really difficult to get up into this area. So because most are in here, and so we're even above that. So so yeah, it makes sense in terms of the placements. Okay, so one step further that you can go with z-scores. Remember that the normal probability distribution, it's an area of 1, right? So what you can do is you can go back to the back of your book, pages 545 through 549, and you can find the z-score of 2.09 in the chart. Like down here, it's not readable, but there it is. Or 2.0. This one doesn't even break it up completely, but the back of the book has it broken up. You can find 2.09, and then you can see the area above the z-score and the area below it. And it just kind of helps you visualize and see the actual numbers to the right and left of the z-score. So that's an additional feature of z-scores. And so you can kind of rope it back into this whole idea of probability and this whole idea of taking up an area, and the normal probability distribution is an area of 1. All right, so let's do some practice with z-scores and calculating them. So let's watch 2 videos. This video, the instructor speaking asks you to pause when you need to be able to calculate the score. So go ahead and listen to him and pause when you need to practice. So, but I'm going to go ahead and let it play all the way through. So again, pause when you need to.
Most commonly used tools in all mean from the data point, and then most commonly used tools in all of statistics is the notion of a z-score. And one way to think about a z-score is it's just the number of standard deviations away from the mean that a certain data point is. So let me write that down. Number of standard deviations, I'll write it like this, number of standard deviations from our population mean for a particular data point. Now let's make that a little bit concrete. Let's say that you're some type of marine biologist and you've discovered a new species of winged turtles. And there's a total of 7 winged turtles. The entire population of these winged turtles is 7. And so you go and you're actually able to measure all the winged turtles. And you care about their length. And you also want to care about how are those lengths distributed. Lengths of winged turtles. All right. And let's say, and this is all in centimeters. These are very small turtles. So you discover, and these are all adults, so there's a 2 centimeter one, there's another 2 centimeter one, there's a 3 centimeter one, there's another 2 centimeter one, there's a 5 centimeter one, a 1 centimeter one, and a 6 centimeter one. So we have 7 data points, and from this, and I encourage you at any point if you want, pause this video and see if you want to calculate, what does the population mean here? We're assuming that this is the population of all the winged turtles. Well, the mean in this situation is going to be equal to, you could add up all of these numbers and divide by 7, and you would then get 3. And then using these data points and the mean, you can calculate the population standard deviation. And once again, as review, I always encourage you to pause this video and see if you can do it on your own, but I've calculated that ahead of time. The population standard deviation in this situation is approximately, I'll round to the hundredths place, 1.69. So with this information, you should be able to calculate the z-score for each of these data points. Pause this video and see if you can do that. So let me make a new column here. So here I'm going to put our z-score. And if you just look at the definition, what you're going to do for each of these data points, let's say each data point is x, you're going to subtract from that the mean, and then you're going to divide that by the standard deviation. The numerator ID over here is going to tell you how far you are above or below the mean, but you want to know how many standard deviations you are from the mean. So then you'll divide by the population standard deviation. So for example, this first data point right over here, if I want to calculate its z-score, I will take 2. From that, I will subtract 3, and then I will divide by 1.69. I will divide by 1.69. And if you got a calculator out, this is going to be -1 divided by 1.69. And if you use a calculator, you would get this is going to be approximately negative 0.59. And the z-score for this data point is going to be the same. That is also going to be negative 0.59. One way to interpret this is a little bit more than half a standard deviation below the mean. And we could do a similar calculation for data points that are above the mean. Let's say this data point right over here. What is its z-score? Pause this video and see if you can figure that out. Well, it's going to be 6 minus our mean, so minus 3. All of that over the standard deviation. All of that over 1.69. And this, if you have a calculator, and I calculated it ahead of time, this is going to be approximately 1.77. So more than 1, but less than 2 standard deviations above the mean. I encourage you to pause this video and now try to figure out the z-scores for these other data points. Now, an obvious question that some of you might be asking is, why? Why do we care how many standard deviations above or below the mean a data point is? In your future statistical life, z-scores are going to be a really useful way to think about how usual or how unusual a certain data point is. And that's going to be really valuable once we start making inferences based on our data. So I will leave you there. Just keep in mind, it's a very useful idea, but at the heart of it, a fairly simple one. If you know the mean, you know the standard deviation. Take your data point, subtract the mean from the data point, and then divide by your standard deviation. That gives you your z-score.
Okay, so I hope you're able to practice calculating some. We can watch another one as an example of calculations. And this one, they're going to do 4 different calculations. It's the same person. So let's watch it now.
Problem from CK12.org's AP Statistics Flexbook. It's an open source a textbook essentially. I'm using it essentially to get some practice on some statistics problems. So here, number 2, the grades on a statistics midterm for a high school are normally distributed with a mean of 81 and a standard deviation of 6.3. All right. Calculate the z-scores for each of the following exam grades. Draw and label a sketch for each example. We could probably do it all on the same example, but the first thing we'd have to do is just remember, what is a z-score? What is a z-score? A z-score is literally just measuring how many standard deviations away. How many standard deviations away from the mean. From the mean. From the mean, just like that. So we literally just have to calculate how many standard deviations each of these guys are from the mean, and that's their z-scores. So let me do part A. So we have 65. So first we can just figure out how far is 65 from the mean. Let me just draw one chart here that we could use the entire time. So if this is our distribution, see, we have a mean of 81. So we have a mean of 81. That's our mean. And then a standard deviation of 6.3. So our distribution, they're telling us that it's normally distributed. So I can draw a nice bell curve here. They're saying that it's normally distributed, so that's as good of a bell curve as I'm capable of drawing. This is the mean right there at 81. And the standard deviation is 6.3. So one standard deviation above and below is going to be 6.3 away from that mean. So if we go 6.3 in the positive direction, that value right there is going to be 87.3. If we go 6.3 in the negative direction, where does that get us? That goes to what? 74.7? 74.7, right? If we add 6, it'll get us to 80.7, and then 0.3 will get us to 81. So that's one standard deviation below and above the mean, and then you'd add another 6.3 to go 2 standard deviations, so on and so forth. So that's at least a drawing of the distribution itself. So let's figure out the z-scores for each of these scores. So 65, or each of these grades. 65 is how far? 65 is, it's maybe going to be here someplace. So we first want to say, well, how far is it just from our mean? From our mean. So the distance is, we just want a positive number here. Well, actually, you want a negative number because you want your z-score to be positive or negative. Negative would mean to the left of the mean, and positive would mean to the right of the mean. So we say 65 minus 81. So that's literally how far away we are, but we want that in terms of standard deviations. So we divide that by the length or the magnitude of our standard deviation. So 65 minus 81, let's see, 81 minus 65 is what? It is 5 plus 11, it's 16. So this is going to be minus 16 over 6.3. And take our calculator out. And let's see, if we have minus 16 divided by 6.3, you get minus 2.54. So approximately equal to minus 2.54. That's the z-score for a grade of 65. Pretty straightforward. Let's do a couple of more. Let's do all of them. 83. So how far it is away from the mean? Well, it's 83 minus 81. It's 2 grades above the mean. But we want in terms of standard deviations. How many standard deviations? So this was part A. A was right here. This was we were 2.5 standard deviations below the mean. So this was part A. 1, 2, and then 0.5. So this was A right there, 65. And then part B, 83. 83 is going to be right here, a little bit higher. We're right here. And the z-score here, 83 minus 81, divided by 6.3, will get us, let's see, clear the calculator. So we have, well, 83 minus 81 is 2, divided by 6.3, it's 0.32, roughly. So here we get 0.32. So 83 is 0.32 standard deviations above the mean. And so it would be roughly 1/3 of the standard deviation along the way, right? Because this was one whole standard deviation. So we're 0.3 of a standard deviation above the mean. Choice number C. Or not choice, part C, I guess I should call it. 93. Well, we do the same exercise. 93 is how much above the mean? Well, it's 93 minus 81 is 12. But we want it in terms of standard deviation. So 12 is how many standard deviations above the mean? Well, it's going to be almost 2. Let's take the calculator out. So if we get 12 divided by 6.3, it's 1.9 standard deviations. It's a z-score. Its z-score is 1.9, which means it's 1.9 standard deviations above the mean. So the mean's 81. We go one whole standard deviation, and then 0.9 standard deviations, and that's where a score of 93 would lie right there. Its z-score is 1.9. All that means is 1.9 standard deviations above the mean. Let's do the last one. I'll do it in magenta. D, part D. Score of 100. A score of 100. We don't even need the problem anymore. A score of 100. Well, same thing. We figure out how far is 100 above the mean. Remember, the mean was 81. And we divide that by the length or the size or the magnitude of our standard deviation. So 100 minus 81 is equal to 19 over 6.3. So it's going to be, a little over 3 standard deviations. And in the next problem, we'll see what does that imply in terms of the probability of that actually occurring. But if we just want to figure out the z-score, 19 divided by 6.3 is equal to 3.01. So it's very close, 3.02 really if I were to round. So it's very close to 3.02. Its z-score is 3.02, or a grade of 100 is 3.02 standard deviations above the mean. So remember, this was the mean right here at 81. We go 1 standard deviation above the mean, 2 standard deviations above the mean. The 3rd standard deviation above the mean is right there. So we're sitting right there on our chart, a little bit above that. 3.02 standard deviations above the mean, that's where a score of 100 would be. And you can see the probability, the height of this, that's what the chart tells us. It's actually a very low probability. And actually, it's not just a very low probability of getting something higher than that, because we've learned before in a probability density function, the probability, if this is a continuous, not a discrete,
the probability of getting exactly that is 0 if this wasn't discrete. But since this is a scores on a test, we know that it's actually a discrete probability function. But the probability is low of getting higher than that, because you can see where we sit in the bell curve. Well, anyway, hopefully this at least clarified how to solve for z-scores, which is pretty straightforward mathematically. And in the next video, we'll interpret z-scores and probabilities a little bit more.
Okay, so that last video was good at showing how multiple z-scores can be on a one distribution, how you can compare multiple single scores within one data set on a distribution. This last video explains how, because of the fact that z-scores are being placed on a normal distribution, and z-scores are a standardized measure that can be used across data sets. Because of that, you can compare a score on one unit of measurement compared to a score on a different unit of measurement and see how they compare with one another. So that's a really, really crucial and important way that z-scores are used in statistics and used in decision making. So let's watch one last video that explains this process.
Students need to take an exam called the LSAT. Before applying to medical school, students need to take an exam called the MCAT. Here are some summary statistics for each exam. So the LSAT, the mean score is 151 with a standard deviation of 10. And the MCAT, the mean score is 25.1 with a standard deviation of 6.4. Juwan took both exams. He scored 172 on the LSAT and 37 on the MCAT. Which exam did he do relatively better on? So pause this video and see if you can figure it out. So the way I would think about it is, you can't just look at the absolute score because they are on different scales and they have different distributions. But we can use this information if we assume it's a normal distribution or relatively close to a normal distribution with a mean centered at this mean. We can think about, well, how many standard deviations from the mean did he score in each of these situations? In both cases, he scored above the mean, but how many standard deviations above the mean? So let's see if we can figure that out. So on the LSAT, let's see, let me write this down. On the LSAT, he scored 172. So how many standard deviations is that going to be? Well, let's take 172, his score, minus the mean. So this is the absolute number that he scored above the mean. And now let's divide that by the standard deviation. So on the LSAT, this is what? This is going to be 21 divided by 10. So this is 2.1 standard deviations. Deviations above the mean. Above the mean. You could view this as a z-score. It's a z-score of 2.1. We are 2.1 above the mean in this situation. Now let's think about how he did on the MCAT. On the MCAT, he scored a 37. The mean is a 25.1. And there is a standard deviation of 6.4. So let's see, 37.1 minus 25 would be 12, but now it's going to be 11.9. 11.9 divided by 6.4. So without even looking at this, so this is going to be approximately, well, this is going to be a little bit less than 2. This is going to be less than 2. So based on this information, and we could figure out the exact number here. In fact, let me get my calculator out. So you get the calculator. So if we do 11.9 divided by 6.4, that's going to get us to I'll say approximately 1.86. So approximately 1.86. So relatively speaking, he did slightly better on the LSAT. He did more standard deviations, although this is close. I would say they're comparable. He did roughly 2 standard deviations if we were round to the nearest standard deviation, but if you wanted to get precise, he did a little bit better, relatively speaking, on the LSAT. He did 2.1 standard deviations here, while over here he did 1.86 or 1.9 standard deviations. But in everyday language, you would probably say, well, this is comparable. If this was 3 standard deviations and this is 1 standard deviation, then you'd be like, oh, he definitely did better on the LSAT.
Okay, I hope that video was helpful. I think that that's the most impressive part of z-scores, and how it's most useful is being able to compare it across data sets. It's just something that's very useful, and I think that that's how you would use z-scores most as a statistician. So that's it for this week's lecture. If you have any questions, please let me know. Thank you.